Namaskar my dear friends. So we have seen the design and details of this particular switching regulator, which is LT8604. So we have completed the design and details of this particular IC using the data sheet, right? We saw each and every applications of this, like basically it has industrial sensor application or industrial internet of things, or it has some automotive housekeeping supplies, and it can take up to voltage of 42 volt and give you an output of 120 milliamperes rating, right? We have seen the one typical application as well as what is the different process of designing the particular circuit for this particular IC. Okay, so now what we'll do is we'll quickly jump into the typical application that is given by this data sheet itself, and we'll try to explain each one of them one by one. Okay, so let's move to the typical application that is given. All right, so let us say we have a application requirement of, as you can see, this can take up to like 5.9 volt to 42 volt and can give you the output of 5 volt with 120 milliamperes of rating, right? Now what are the things that we need to like keep in mind to design this particular converter so that we have a proper like output, right? So for that what we will do is, first of all, we'll just take this circuit in here. Okay, now let us say we have an input of 12 volt and we have to have the output of 5 volt 120 milliamperes. So first of all we have to design our C input. So input capacitor we have to design, then we have to design output capacitor. So I'll tell you basic understanding about input capacitor and output capacitor of this particular IC, so that what you can do is always have this particular arrangement. Try to have input capacitor of, let's say, 22 microfarad, 22 microfarad, 0.1 microfarad at the input side, and at output side also, if you want, you can keep the same values, 22 microfarad, 22 microfarad and 0.1 microfarad for 5 volt application. Okay, so that is one thing. Otherwise you can keep the input like even 10 microfarad also. Two capacitors should be fine, 10 microfarad, 10 microfarad, with have the proper voltage rating at the input side, minimum of 25 volt. Okay, or you can go ahead with 35 volt ratings. So that is there. In output side you can keep up to like minimum 16 volt rating or 25 volt rating. So in general you can keep 25 volt rating both side, input side as well as output side. Okay, making the design little bit less costly or something like that, what you can do is you can utilize electrolytic capacitor at the input side of, let's say, 100 microfarad with 35 volt rating, and same way 100 microfarad with 35 volt rating at the output also this will do. If you want, you can reduce the voltage rating of the capacitor at the output side to 25 volt also, but I'll suggest to keep you at the same voltage so that you can have less number of like components, and you can reduce the cost as well. Okay, so coming back to the design of this particular circuit, so you understood C input, you understood C output. Okay, so they have already given 10 microfarad. What you can do is additionally you can put one more 10 microfarad. Let us say I'll just remove this and put it one more 10 microfarad and then 0.1 microfarad. So your job will be done. Okay, like that you can do. Similar to that, input side also you can keep two more capacitor with 22 microfarad. That is more than enough. Understood? So this is your input. Now coming back to the int VCC, so this is a regulator for internal purpose, so you just put 1 microfarad capacitor and put to the ground. Okay, coming back to the soft start, so soft start you can keep 10 nanofarad of capacitor to the ground. Coming back to the switching frequency working, so switching frequency working you already know, we have a series of resistors. Okay, just let me make it little smaller. Okay, so as you can see we have, yes, so we have switching like a regulator switching frequency resistor setting. So for 700 megahertz, like 700 kilohertz, you have to have 60.4 kilo ohm, or otherwise what you can do is, if you want to work with lower frequency, let's say 500 kilohertz, you can keep 86.6 kilo ohm. or if you want to work with 1.2 megahertz, then you can keep 33.2 33.2 kilo ohm. Okay, so this is the understanding that you should have. Okay, so we have, let's say we have set the switching frequency to 700 kilohertz itself. Now coming back to the output side, so output side there is a regulated voltage of 5 volts. So for that we have to design our R1 and R2. So keeping in mind that R1 R2 value should be as high as possible, so that you don't lose the current in this side, and efficiency will be little bit higher. Okay, that's the data sheet recommendation as well. Okay, so for that purpose, let us do one thing. We will just calculate this particular feedback resistance in our Excel sheet. So what I have done is, V output I have set it to 5 volt. Let me just increase this so that you can see it properly. Okay, so as you can see, I have set it to 5 volt. Now FSW is set to 700 kilohertz, and VFW feedback voltage was set to 0.778 volt. Let us say I am going to choose R2 value as 100 kilo ohm, then R1 value will be calculated to 543 kilo ohm. Okay, so this is how you can have. Let us say I am going to choose R2 value as 187 kilo ohm, then this will be close to 1 mega ohm, that is 1014 kilo ohm. Okay, so this is how they have calculated. So let's say I am going to put 150 kilo ohm, then it will be 114 kilo ohm, so that you can put it. So closer to this value, a standard value, you can keep it 110 kilo ohm or something like that. So what we will do, we'll just change it to let us say 100 kilo ohm, and for 100 how much it was coming, let's say 100, then it was coming 543 kilo ohm. So we'll put it 543 kilo ohm. Understood? So this is the understanding of R1 R2 value for the feedback resistor, so that you can set the output voltage to 5 volt. Now what else is remaining? We have to find out the inductor value for that region. So for inductor value, we had the option of finding the minimum inductance value, okay, using this formula. So if you see, minimum inductance that will be needed is 89 microhenry. Okay, and a good start of this particular inductor calculation was this formula. Okay, so V out plus VSW bottom divided by FSW into multiplied by 20, right? So for that you are getting 146 microhenry. But at the same time, if you are working with duty cycle more than 50%, let us say my duty cycle is 50% or higher, then you can also keep the minimum value requirement of inductor was this much, which is coming around 91 microhenry. So it is always a good understanding of keeping more than this is a good understanding. Okay, so that's the reason we are going to set this to 100 microhenry. Okay, so we have understood the value of how to calculate the value of inductor, and at the same time the output capacitor requirement will be minimum 14 microfarad. That's the understanding. Okay, so you can see this is the formula that we have used, 50 divided by V output into FSW. So that is going to give us 14 microfarad. Okay, so 14 microfarad or more than that will be needed at the output side to have the proper output. Okay, so since derating curve of capacitor, if you see, basically as you apply the voltage here, like V supply, okay, then the capacitance value actually decreases. So let's say this is 100%, so this reduces a little and it goes down. Okay, so that's the reason we always prefer to use little bit higher capacitance value, so that you don't lose the capacitance at the applied voltage. Okay, so we'll just set it the inductor value to 100 microhenry, and this is the boost capacitor. So boost capacitor for internal MOSFET, like this thing, so that we have set it to 47 nanofarad. Okay, now only one pin which is remaining is our power good indicator. So power good indicator, if you want, you can utilize it, otherwise you can leave it open also. So let us say we use it. Okay, so we can set it to 5 volt with 100 kilo ohm, or even 47 kilo ohm or 20 kilo ohm or 10 kilo ohm, anything is fine. Okay, for that matter, and send this to your microcontroller GPIO. So that microcontroller pin will be acting as an input pin, and it will indicate whenever it goes low, then it will tell you that the output voltage is not into the proper region. Okay, or it is not in proper regulation mode, right? And if it is high, then it will tell you that it is in good condition. Just make sure that the microcontroller pin that where you are sending it has a capacity of taking 5 volt tolerant, otherwise it will not work out properly. What you can do is, if you have a 3.3 volt available in your board, then you can pull it up to 3.3 volt also, so that it will work for any GPIOs for that matter. Okay. Coming back to the input enable pin. So enable pin, what you have to do is, if you are not using the enable voltage, like under voltage lockout, like you don't have a criteria of starting the regulator at a particular voltage, once it reaches to, let's say, 5 volt, or like let's say 8 volt or something like that, you can directly connect this particular enable pin to input pin. That's all. So this is a very straightforward understanding. Good. So hope you have a good understanding, and always keep in mind the input capacitor and output capacitor have this option as well. Even if you're not using, like 2 capacitor plus 1 more capacitor, you have the option of minimum 3 capacitors at the input and minimum 3 to 4 capacitors at the output, so that you can always increase the value of capacitance based on the load that is required. Okay. Okay, good. Now let us move to the another application. So quickly we'll move to the another application, which is going to be 3.3 volt. Now they are telling you that it is going to work on 2 megahertz. So if you want, you can reduce the like switching frequency. So for that you have to change the value of RT resistance, and accordingly you can design. I'll tell you very simply, the input capacitor, as what you designed for 5 volt, you can utilize the same values. That will not be a problem at the input. At output, what you can do is, you can increase the C output a little from the 5 volt that you had used. Okay, so you can keep, like 3 to 4 capacitors at the output with 0.1 microfarad capacitance additional. Okay, and rest other values you can keep it as it is, like int VCC and soft start capacitors, or like boost capacitors, bootstrap capacitors, or the inductor value and resistor feedback. These two things I'll just calculate and show it to you what will be the values for this, let's say R1 and R2, and this is my inductor value. Okay, so let's get into the Excel sheet. Now we are going to put this output voltage to 3.3, and let us say we are going to work with let's say, first I'll show it to you with 2 megahertz, that is 2000 kilohertz. You are going to get the inductor value to be how much? Let us say more than 21 microhenry, or like L start can be 34 microhenry. Okay, so for that 33 microhenry will be a good choice. So what we can do is, we can utilize 33 microhenry. So yes, very good calculation, right? So 33 microhenry is a good choice. Okay, now let's talk about this R1 and R2. So as I told you, like if I am going to use R2 as 100 kilo ohm, then R1 had come to be how much? 325 kilo ohm or something like that you can utilize. Okay, so for that purpose, what we can do, we can use 100 kilo ohm and 325 kilo ohm. Okay, let us say I am going to calculate 309 kilo ohm, then it will come 1 mega ohm. I'll just show it to you. 309 kilo ohm, then you are going to take going to get your R1 value as 1001 kilo ohm. So if you want, you can utilize the same values. Otherwise, if you want, you can reduce this value to, let's say, 220. Accordingly, you have the value, other value is 710 kilo ohm. You can utilize closer value. Okay. Good. So the another application is done. Let's move to the next one. So I'll suggest you keep the FSW like around 700 kilohertz. That is actually good value. Otherwise, maximum you try to work with 1.2 megahertz. Don't go beyond that. It is like good for better efficiency. Okay, so the only change that they have done for this 5 volt with 2 megahertz is, this was the 5 volt 700 kilohertz. Okay, now the only change that you will see is 18.2 kilo ohm. Okay, so this is the same what is that application with higher switching frequency, and as you can see, only change that will come due to this particular switching frequency is the inductor value. So earlier the inductor value we had used 100 microhenry for 700 kilohertz of operation. Now we had increased it to 2000 kilohertz, that is 2 megahertz. Then my inductor value has reduced to 47 microhenry. Okay. So what shall we do? Shall we try it out, like whether we get around 47 microhenry for 2000 kilohertz of operation? So let's open the Excel sheet of our calculation and let's set the output voltage to 5 volt. We are going to set the switching frequency to 2000 kilohertz, that is 2 megahertz. And as you can see, my inductor value, that is minimum is required, is 31 microhenry and L start is around 51 microhenry. So you can see between 32 or L minimum 2 is, like you can see L minimum was one more is there here. Okay, for duty cycle more than 50%. Okay, so in that case you can see it should be more than 32 and around 51 microhenry. So that's the reason 47 is a good choice. So 47 microhenry was chosen for that matter. So good, 5 volt with 2 megahertz of operation, 47 microhenry was a good choice. And if you want, you can keep the resistor divider same values. Otherwise, you can change as the previous one what we did, 100 kilo ohm and 543 kilo ohm. Okay. Good. Let's see quickly the other applications. So we have one more is 1.8, or let me get into the data set itself, that is little better. Okay. We have a operation of like 1.8 volt regulator. So let us say input voltage is 12 volt, or input voltage is even like 5 volt or 3.3 volt. All will work for this purpose because it is like 1.8 volt. So you need 1.8 plus around 0.9 volt just to have the input. No, but one thing you have to understand is input cannot be less than 3.2 volt. Okay, so 3.3 is the minimum that will be needed, so that is good. Okay, you cannot work with less than 3.2 volt. Okay, that was there in the data sheet. So C input, as you can see, you have to have the same values almost, C in values. Okay, C output values will be increased a little higher values. Okay, so you can keep 47 plus one more 47 you keep, and plus 0.1 you keep. Okay, so 47 one more and then 0.1 one more. Okay, so that's the understanding, like since our output voltage has reduced, then our capacitance must be increased in the same ratio, so that it will be not going to have lot of ripples. Okay. Coming back to the like switching application. So switching application operation, they have told like they are going to work with 400 kilohertz, let us say. So accordingly RT value will be calculated to 110 kilo ohm. Okay, so as you can see here, for 400 kilohertz the RT value is 110 kilo ohm. Okay, now let me just set the output voltage to 1.8 and let's set the switching frequency to 400 kilohertz. So as you can see, for 220 kilo ohm of R2, R1 will be 288 kilo ohm. Okay, or let us say what is the value that they have used, 768 kilo ohm of R2, R1 will be close to 1 mega ohm. Okay, so let's say I'll put 768 kilo ohm, it will be close to 1008 kilo ohm, that is 1 mega ohm. Okay, and you can see L minimum should be like 60 microhenry, or like a start value is coming to be 97 microhenry. So you can keep more than 61 or like 62 microhenry, that's the reason they have used 63 microhenry or 68 microhenry. Yes, so 68 microhenry is also a good choice. Understood? So hope you guys are like understanding, and you guys have an idea of like how to set the values of input capacitor, how to set the values of output capacitor, how to set the values of feedback resistance divider. Okay, to regulate the output voltage to be proper. Okay, and how to calculate the inductor values, and all these boost capacitors like bootstrap capacitor or like bias voltage. See, you can see the external source, if it is more than 3.2, then you can directly put it a ground, that is another thing. Okay, so this is how you are going to design a proper circuit for your requirement. The only changes that you are doing is the switching frequency you are reducing or increasing, based on that the L values is increasing or decreasing. Okay, so let me quickly show it to you. Let us say I want to work with 700 kilohertz, which is like optimal value I feel. Okay, so for that you can utilize still like 33 microhenry, 35 microhenry or more than that, or 55. So 47 microhenry will be a good choice. Okay, so if you want to work with let us say 700 kilohertz, the corresponding L values will be coming as 47 microhenry. Okay, so this is how you can reduce the inductance value based on the switching frequency of higher order. Okay, good. Let's get into the another application. C input you try to keep same, C output you try to keep same. Okay, just increase a little more. Okay, this is 2.2 is very less. Okay, so keep one more plus 0.1, one more. Let us say you keep here 22 microfarad. Okay, additional 22 microfarad you keep. Input capacitor, as I told you the previous sections, 22 plus 22 plus zero point 0.1 is more than sufficient. Now let us say we have to have a 12 volt output, so accordingly we have to calculate the inductance value, and for that purpose we have to decide what is the let us say my input value is 15 volt and or otherwise 18 volt or 24 volt or even 36 volt or 30 volt, whatever is the case. Okay, now with this particular setting we'll try to show it to you. It is coming to 220 microhenry. Okay, so let me set the output voltage to 12 volt. Okay, and the switching frequency is how much? It was 1.2 kilohertz, right? 1 megahertz. So 1 mega is 1000 kilohertz. So accordingly you can see the inductance value is coming to be more than 151 microhenry or around 242 microhenry. That's the reason they have chosen 220 microhenry. Okay. Now let me do one thing. I'll just work with 700 kilohertz. So in that case you can see the inductance value is reduced to, oh, it has increased. So wait a moment. Yes, of course, like if I reduce the switching frequency to let's say 700 kilohertz, my inductance value should increase, right? That's the reason my inductance value has gone to 346 microhenry. Okay, so if you want you can still work with 330 microhenry or something like that. So 330 microhenry will be a good choice for this particular application. Okay, but since the output voltage is quite high, so we'll try to work with little bit higher switching frequency so that we can reduce the inductance value. Okay, and this feedback resistance, if you want you can keep it same values, because they are always trying to keep this R1 value to be 1 megahertz, 1 mega ohm. Then R2 value is calculated accordingly, and since I am choosing R2 value, then R1 value is getting calculated accordingly. Okay, so let me just give you a calculation also for this. So for 12 volt, what will be my R2 and R1? So let me say that my R1 value is R2 value is 100 kilo ohm. So according to that you can see 1.44 mega ohm is coming. Okay, or if you want you can reduce it to let's say 76 kilo ohm or 75 kilo ohm. Then you can keep it 1.08 mega ohm. Okay, or 1081 kilo ohm. So closer to this value you can utilize, or exactly they have utilized how much? 69.8 kilo ohm. So for 69.8 kilo ohm you can see we have 1000 kilo ohm, that is 1 mega ohm. Okay, alright. So as you can see, what are the variation that is coming up? The output voltage settings, that is one thing. Based on that, accordingly my feedback resistors divider is changing and the inductance value is changing. Inductance value is changing based on one more parameter, which is the switching frequency of operation. Okay, and accordingly my input capacitance and output capacitance are changing. As my output voltage is going higher, my output capacitance can be reduced a little. Okay, so that we don't have a problem of like ripples. Coming back to the next applications, so let us say we want to set it to hysteresis also. So C is for hysteresis. Okay, so in that case what they have done is you can utilize, let us say this is my R3, this is my R4, and this is my R5, and this is my R1, this is my R2. According to that you can calculate whatever way you want it. Okay, so hope you are able to see this. This is my R3. Okay, Now what is the thing that is there? We have 5 volt 2 megahertz, so 2 megahertz we already saw. So only change that is going to have is our enable voltage lockout. So instead of connecting directly to input voltage, we can have enable pin or enable voltage lockout. So for that enable voltage lockout, what you can do is you can have a calculation of this thing. Let us say I have 12 volt input and I want to switch it on when my enable voltage reaches to 7 volt, or let's say I'm making it 9 volt. So for that, let us say my R4 is set to 1.5 mega ohm, that is 1500 kilo ohm. Then my R3 will be going to come up as 11.4 mega ohm. Okay, so you can see how much is that. 1.5 it is done, then it is going to have 8.45. So 8.45 is calculated based on the enable voltage is 7 volt. Okay, so if you put 7 volt, let me just tell it to you. If you put 7 volt, then how much it should come? 8.5 or something. So it is coming 8.5 mega ohm. Understood? So they have used 8.5. 8 point how much they have used? They have used 8.45. Okay, so they have used lesser than that. It means it will be little bit higher, because if you can see, the enable voltage rise is getting calculated to how much? I will just show it to you. This one. Okay, so if you calculate this one, then you can see how much it is coming. It is coming to be 7 volt. Okay, so it will appear, it will switch on at 7 volt. If you want, you can reduce this voltage. So once you reduce this R3, then what will happen? Based on this condition, if you are seeing, if you increase this value, this is increased, right? 8.5 is more than 8.45. I have used in the circuit 8.45 mega ohm. Okay, so if you reduce this R3 value, then my enable voltage lockout will be reduced a little. So it will come around how much? 6.7 or 6.8 volt. Okay, so this was the change with this particular circuit. Going to the next one, let us say 1.8 volt with this LT8604C. So in that, what will happen? You can directly connect your enable pin to the input voltage if you don't need enable voltage lockout or under voltage lockout. Coming back to the other parameters, same. You don't have to worry about at all. What will be happening? Your input capacitor you design as usual. Your output capacitor design as usual, like whatever I told you in 1.8 volt previous one. Okay, and then we have a feed forward capacitor that is added, which you can add in all the other circuits also, here also, or like other ones also. So wherever is there, you can add this feed forward capacitor. It helps you to smoothen the output voltage. Okay, then voltage feedback resistance divider, you can design accordingly what we did. Then based on the switching frequency, like switching frequency is 1 megahertz, accordingly my inductance value will be calculated. Okay, if you want, you can decrease this value, so accordingly this inductance value will be increased. Understood? Good. And this bias voltage only change is happening is, as you see, this bias voltage is actually connected to V out whenever the output voltage is more than 3.3 volt. Okay, so the only change that is coming is bias voltage is connected to output whenever the output is more than 3.3, and when it is less than that, then what you can do is you can directly put one capacitor to the ground, since my output voltage is not more than 3.3. That is, yeah, it is just like external source should be 3.2, then only it should be connected, otherwise it should be grounded. That was given in the data sheet. So let guys, hope you have a good understanding of all these circuits that we have shown here. Okay, and if you do have any questions regarding this particular applications, or how to have a particular design based on your input voltage, because this variation will not be there in your input generally. You might have like a 5 volt input here, or 12 volt input here, or let's say you have a battery input which will be varying from, let's say, 9 volt to 14 volt. So that can be the variation, that's all. Or even it can go as high as, let's say, 36 volt, because there's some power supplies are there with 36 volt or 30 volt or even 24 volt. So these are the standard power supplies that are generally available at the input side. So you will not be having continuous variation from 3.2 volt to 42 volt. You will be having a specific value at the input. Similar to that, you will be requiring 1.8 volt logic output for some sensor application, or even 5 volt or 3.3 volt, or some sensors are, let's say, working with 12 volt output with lower current ratings. So in that case, this particular IC can be utilized. Okay. And same manner, you take any IC for your application, same manner you have to utilize, like what should be the input capacitor, what should be the output capacitor, what should be the inductance value, what should be the, like, feedback resistance calculation based on the formula that is there in the data sheet itself. How we can have a power good indication monitor, whether you want to monitor through an LED. So otherwise, LED, if you want, you can connect one LED directly. So whenever this is in good condition, like output is around 5 volt plus minus 1%, then it will be glowing. And if it goes beyond that, basically the feedback voltage is varying beyond the region, beyond the specified values, then it will go low, and there your LED will go low, like LED will go switch off. So in that case, you will see that output is not in the proper manner. Okay. So good. If you do have any questions regarding that, please put down your comments in the comment box, and we shall be able to answer you out for your particular applications. Thank you so much.